Hi, welcome to my presentation on two-level radiance caching for fast and scalable real-time global illumination in games. My name is Guillaume, and I'm a graphics programmer at AMD in the Advanced Rendering Research Group. And really, the work I'm presenting here today is the work of all my team. So I thought at least everybody here. And more specifically, I'll be going over the details of our recent GI 1.0 publication that we released late last year, about November 2022. So I'd like to start with a bit of motivation. This is a very simple shot rendered without global illumination. It's made of a single global probe and a bit of ambient occlusion. I'd like to point out that, yeah, it's a very simple render. You can do things that look much better without the need for a fancy dynamic GI system. So I invite you not to read too much into these images, but rather see this as a visual motivation for this presentation. So this is our render without global illumination. And with global illumination, this is exactly the same lighting condition. We've just turned our technique on. And you can note how the correct capturing of short range and long range occlusion really helps grounding the scene elements together. Here's another example without global illumination. And with GI, here I'd like to draw your attention to how the emissive surfaces in particular correctly cast light and shadows onto the surroundings. And final example without GI, and with GI, you can see a bit of color bleeding. So why global illumination? Hopefully the images we've just seen help answer that question. Accurate occlusion can really help ground the scene elements together, and color bleeding can produce richer and more believable lighting, a more believable world, therefore. Now, possibly a more interesting question is why real time? Why do it at runtime? Baked lighting can be pretty high quality. There's lots of techniques available, but obviously it's limited in its ability to adapt to changing geometry and lighting. So we really see the goal of calculating GI at runtime as a way to allow for more dynamic worlds. And we're not completely there yet. I'll touch back upon that topic later in the presentation, but that's really our aim. And another benefit is that it can improve content creation workflow by making iteration faster and more pleasant, where you always work against the like an up-to-date state of the lighting, and I'll have to wait for a bake process as you author an environment. Ray tracing is finally available in hardware, so we're going to use this for our purposes, but it remains expensive. So we need to find solutions that can achieve high lighting quality, but at reduced sample rates. And this is a very active area of research. I've listed a few solutions available in here, but a technique that really caught our eyes about 2 years ago was this screen space radiance caching technique presented by Daniel Wright. It offers an interesting trade-off between path tracing and more traditional probe system with an interesting new twist. This is an image from their presentation comparing a two-sample per pixel path tracer, although not a very good path tracer, quite clearly, against only half a sample per pixel screen probe system, so 4 times less number of rays. This image in particular I thought was very interesting. Having less noise for less samples overall obviously sounds like a good idea. So we've built upon this this technique and we've implemented this this pipeline for real-time dynamic global illumination, which is fundamentally a two-level radius caching system, where we try to have very few rays but make the most of every ray by caching the radiance and then using it for sampling. So you can see the diagram illustrating as the path bounces around the scene are two levels of caching. This is also very much the plan, this presentation. So we'll start with the screen probes, which is our first level of caching. They position directly onto the primary surfaces and only onto the primary surfaces. They cache the incoming radiance across the hemisphere, and they're high fidelity simply by virtue of the fact that we have many probes. We'll see that in a bit. Then the hash cells, they're the second level of caching. They're positioned anywhere in the world. They cache the reflected radiance for a given direction. The file is detailed than the screen probes, but they're stable and persistent, so it's a nice complement. So as mentioned, that's a bit the plan of the presentation as well, so we'll start with the screen probes. Screen space radiance caching. The goal here is to evaluate the lighting at X point on our primary surface after hitting the primary ray. In our implementation, we trace, between quotes, the primary rays using rasterization. It's not compulsory, obviously, you can use ray tracing for this. And then the goal is to store the incoming radiance across the hemisphere into a probe. We use octahedral mapping for this, but you can use any kind of projection, really. Then once we've got the probes, we go over every pixel, find the 4 neighbor probes, and we can interpolate the lighting. So it's quite a simple technique conceptually, but interestingly, it fixes quite a bunch of issues that have been big problems for traditional probe systems like 3D grids of probes. When you make grids of probes, like 3D grids of probes, placing the probes is really important and particularly difficult. When it comes to screen probes, the placement is trivial. We always know exactly what the probes are with regard to the geometry because they're placed on the depth buffer, so they're literally on the geometry, which makes it easier to get rid of light and shadow leaks. And second point, density is also really important to get right in a more traditional probe system. And again, with the screen probes, this is a bit of a non-problem. It's necessarily optimal for a given viewpoint. There's no computation wasted on non-contributing probes because we only have probes for what's on screen. And because the grid is pretty dense, we're able to capture smaller details of nearby occluders and therefore achieve a higher quality lighting. So a key aspect of our technique, the way we've implemented it, is this temporal upscale. We've decided to cache up to 1 8x8 probe for every 8x8 tile on screen. This choice is pretty arbitrary, but it has the nice property that our probe grid is essentially the same resolution as a render target, but aligned to the next multiple of 8. You can make other choices, but that's what we did in our implementation. Now, recalculating everything would require 1 ray per pixel, which is too expensive. So we only recalculate a quarter every frame, and then we rely on upscaling over multiple frames, what these images are showing here. First frame, we get lots of holes. After 4 frames, we've got the full grid. This amount of 1/4 is completely arbitrary. You can go higher, which will make the system more reactive. Or you can also go lower, which will be quite a bit faster, but you'll suffer from higher latency, in particular when it comes to reacting to light changes. Overall, however, the final image quality is not impacted much. Once the temporal upscale has completed. And here I want to point out that this reduced rate does not apply only to ray tracing, although that's a big important factor behind this decision, but it also applies to all sampling and filtering of our probe grid. They all happen at reduced rates, so it's very important performance speed up. The only two passes that run at full rate are the reprojection pass, which we're going to see now, and the interpolation pass. So temporal reprojection of this probe grid. We do this in a single dispatch that's conceptually made of two distinct parts. And as I mentioned, we go over every pixel at target resolution. And I think now is probably a good moment to clarify what I mean with target resolution. In our implementation, it's the resolution of the G buffers, depth, normals, and so on. Probably doesn't have to be this way. It could be decoupled further, but we expect that it's going to be a common choice of implementation. But the important point is that it's not necessarily equal to the output resolution. You can use super resolution effects such as FSR, for instance. The challenge, anyway, of reprojecting our set of probes is that we've got a sparse number of probes in frame t-1, and we want to find the best pixel in frame t to place our probe. And it's a challenge because there's multiple candidates, so we need to find the best candidate. So in the first part of the dispatch, we go over every pixel, perform a standard temporal reprojection, locate the nearest probe in the previous frame if we find any, and then determine whether it would be valid using some kind of depth and normal checks to place the probe from the last frame onto this new pixel. So this may not be valid. It's marked as X on the diagram. And if we can, if we estimate it be valid to reuse the probe onto the new pixel, we calculate a reprojection score that effectively quantifies the amount of error in the reuse. Then we want to reduce to the single best candidate. And this is done by encoding the reprojection score onto the top 16 bits of a 32-bit integer and the index of the corresponding lane onto the bottom 16 bits of that integer. And then we can use a single LDS-based atomic mean operation, LDS here standing for local data share. And we can use this operation to reduce down to the best candidate across the group. Then the second part of the dispatch simply reads back the reprojection result from LDS and plays the probe onto the selected new pixel in the current frame. Obviously, this process can fail. Then this is a disocclusion, and we simply flag the tile as such because we couldn't find any suitable candidate. So this is how we reproject the grids. And now we want to spawn our new probes to start getting new data and updating the grid with this new data. We use a fixed global pattern across the screen to spawn the new probes. And as I mentioned, we only calculate a quarter of the probes every frame. Disocclusions naturally will show holes where up to 3/4 of the information is missing, which is what you can see on the left image here. A lot of holes and missing information, which is not good for visual quality. So we could decide to fill the holes by tracing additional rays and allocating them to the red areas of the image. We'd like to keep our ray budget low and constant, however, so instead what we do is we rebalance the rays that the kind of fixed ray budget that we have away from converged probes, that is tiles that have valid data, and towards filling the holes in a stochastic fashion. This gives us less noticeable disocclusions at no extra cost. And the next slide is like explaining a bit how this works in practice. So we start with the results of our reprojection. Here I have a little diagram showing the tiles. The green tiles have succeeded reprojection, the red have failed, there are holes. So we start by pushing out all the holes into a queue, all the empty tiles. Then as we use our fixed global pattern, we push all the spawned tiles, let's call them this way, into a second queue. Here you can see that we spawn a probe onto the top left tile of the 2x2 quad. But while we do this, we also populate a third queue, which we call override tiles, which stores a list of all the probes that we've spawned on tiles that already have valid data. This represents the like the bundles of 64 rays that we may want to deallocate away from their spawn position and towards filling the holes. So now we can go wide over the empty tiles, pick up a random override tile, and with a single atomic exchange, we just patch our list of spawn tiles. So if you look at the top diagram, as I remove the atomic exchange, you can see these two probes in the diagonal are back into their position, and as I re-enable the atomic exchange, they're repurposed towards filling the hole. This is a video showing how it looks in action without adaptive sampling. So you can see this quite a bunch of holes, all these red tiles that we can see across the screen, and turning on adaptive sampling, the holes are greatly reduced, although not completely. Again, this is a stochastic technique, so there's a random chance a hole gets filled or it doesn't. And this is the final render without textures. So we can use the results of our reprojection, of our probe reprojection, to estimate the contents of the new probes without having to trace array. We call this process hemisphere reconstruction, and this is achieved by using the reprojected probes from a 3x3 tile neighborhood. Essentially, we try to, for the new probes which we don't have any data yet, we try and estimate what the hemisphere should look like based on our reprojection. We can use this to guide the new rays when the reconstruction succeeds anyway. If it doesn't, we fall back to uniform sampling, which you can see on this video. So it's fairly noisy. If the reconstruction succeeds, we use it for sampling, and we implement this by storing the cell's luminance in a local data share, scan it into a CDF, cumulative distribution function, and then we can use the CDF to pick a cell proportional to its intensity. So we've got uniform sampling there, and this is the result after our guiding. You can see how the noise is greatly reduced, and that's with exactly the same number of rays, and after denoising. Now, for the guiding to be successful and reduce noise appropriately, we really want the hemisphere reconstruction to be as precise as possible. So I mentioned we use the reprojected probes in a 3x3 tile neighborhood, and what can happen is that if you were to just copy paste the probe data and onto the newly spawned probes, well, lighting parallax may play a significant role, and you may be getting the wrong direction to try and hit your light source, which can make it difficult to hit bright areas consistently. So we perform a parallax correction during the reconstruction, which is implemented by reprojecting the direction into the newly spawned probes and scattering the radiance data using 4 LDS atomics. And then we can simply sync the group, normalize, and resolve the history radiance into the cell. So this is our naive reconstruction, and I'll switch now to the parallax corrected version, and I'll go back and forth between these images, and you can see in particular on like edges of object or rounded surfaces, the parallax correction really helps better guide the rays and hit the light source more reliably. Now, due to our guiding strategy, some cells may not be visited, which would lead to a loss of energy if you leave them black, as on the image on the right. There are multiple solutions for this. we can either decide to trace more rays in a way to make sure that every cell has at least one ray, or we can decide to not trace any extra ray, which is better for performance, and rely more heavily on history instead. So we'd like to avoid option 1 because constant ray budget helps performance, of course, but especially performance stability and predictability. But option 2 introduces strong temporal artifacts. We've tried it, and you get some kind of dark streaks across the screens in some cases. So we went with approximating the missing information, simply done by averaging the radiance from the trace cells again in LDS and distributing the result uniformly across the untraced cells. So this is our naive guiding, and this is with the radiance backup. So you can see how we recover some of the missing energy. And the final render, it's naive guiding, and with our backup, and recover some of that missing energy. So all I've described so far is how do we best spawn our probes on the screen and pick a cell that we want to visit, but we haven't traced the ray yet, so we're going to do this now. Once we've got the cell we want to visit, it's quite easy. We just generate a 2D jitter inside the cell, and we back project this to a world space direction, and now we can trace our ray as the closest hit query. And this leads us to the next point along the path, the point P, and now we want to evaluate the lighting at P, and that's the job of our second level of caching, if you recall the diagram at the beginning. And I'll describe this later, so we're going to skip this for now, and just assume that somehow we know the radiance at P, we get some estimate back. So what we want to do next is blend the radiance estimate with our history. And we found out that using a regular exponential moving average was hurting quality too much. And that's because the probe cells are fairly large. They cover a large area of the scene. So just naive blending across all the radiance estimates leads to excessive blurring of the radiance and a loss of shadows in particular. Instead, we decided to adapt the temporal blending factor. And we do so by using the error, the normalized error, between the history and the new estimate in the way that favors darker samples over brighter ones. This helps stabilize the image temporarily while preserving occlusion and shadows, but at the expense of some image darkening. This is without any guiding, and this scene is particularly challenging because it's pretty much exclusively lit by all those emissive triangles scattered around the scene. When we enable ray guiding, the image is far more stable, but not completely stable. And with our biased hysteresis, it gets quite a bit darker, but we get now a stable image to output on screen. And what this really does, in effect, is it eliminates the light sources that are smaller than the granularity of our guiding, because the guiding efficiency is limited by the probe's resolution. We sometimes may know that something is bright in a given set of direction, but we don't know precisely enough that we can reliably hit it. So we just get rid of that signal, which is better than temporal instability. I should point out that the darkening in this scene is pretty strong, but in other scenes where the lighting is easier to find, then the darkening is far less noticeable, or maybe even not noticeable at all. Okay, so probes I mentioned, they can be on any of the 64 pixels within a tile, and it's important that we track very precisely where they are at a pixel level. So we maintain a probe mask texture for that purpose that stores the pixel position of each probe inside the tile, or an invalid marker if the reprojection has failed, so the red areas in that image. Now, areas with missing probes can be fairly large, which is a bit of an issue because we often want to find neighbor probes, like what's the probe on the left, maybe we want to use information from that one. We want to be able to search across holes efficiently. So we build a MIP chain of the probe mask. This is the first MIP. It's just a direct representation of the previous image. And the MIP chain simply try and keeps the first valid probe from the 2x2 upper value. So when we go to MIP 1, you can see how the red area is shrinking, as well as the resolution. And by MIP 2, we have normal holes. We use the mask to perform large-scale search for probes, which is used extensively during the probe spatial filtering, as well as during the final interpolation pass. Essentially, what you do is once you start at MIP 0, you want to find a probe on the left, so you look to your left. If it's a hole, you recenter onto the original sample, go down a MIP, look to your left, and continue until you find something. So we always end up finding something. Whether you can reuse information from that probe that the system located is another question, but you'll get a probe back. And now we'll see how we implement our spatial filtering at the probe level. It's very straightforward with simple 7x7 separate blur in probe space, using the probe mask to search across holes, and distance to plane kind of bilateral weight to avoid light leaking. As Daniel writes, publication, we also use the angle error after heat reprojection to reduce excessive blurring after probe filtering. So this is a kind of a naive filter, and this is with the angle error check. So I'll go back and forth, and particularly if you look at the sinks, you can see how the shadows are extremely blurred in this version, and they recovered in this one. All right, even after upscaling, we're still fairly undersampled. We only have one probe in every 64 pixels, which is not really an issue as such, because we can interpolate between probes, and that's the purpose of probes in the first place. But thin geometry can cause temporal flickering, which is what I tried to highlight in this diagram. Here we have this wobbly line, which represents a thin feature. It can be some kind of hair or something. And on the first frame, we spawn probe 1 onto the thin feature, and we calculate it, have some radiance data. And then next frame, probe 2 is spawned outside the thin feature, so we can't reuse from probe 1 during the hemisphere reconstruction step. Now I mentioned that we actually use the probes in a 3x3 neighborhood to perform the reconstruction, but we're going to ignore that for the purpose of simplifying this explanation. So probe 2 has to start again from scratch. It's got no history. And finally, probe 3 is back onto the thin feature, and again cannot reuse from probe 2, so it fails the temporal reuse and guiding all over and has to start from scratch again. Which is a bit of a shame, because we had totally valid data only 2 frames ago. What this really causes is that in some cases our guiding reuse is kind of failing every frame in the worst case. So our solution to this is to cache the evicted probes into a persistent queue, which we call the LRU site cache, LRU standing for least recently used. And we detect eviction when a new probe cannot reuse from its center tile. In such cases, we push it out to the queue in a way that we can reuse from all the probes many frames later, an arbitrary number of frames later, actually. So this is a render done without our LRU site cache. And you can see this scene has quite a lot of depth and geometrical discontinuities, which causes quite a few screen probes to start their accumulation from scratch again and generates those fireflies. This is the cached probes. You can see it's a bit of a mess. That's because the queue is constantly reordered based on least recently used usage. So the least recently used cache probes are the ones we evict first. So you get this kind of random ordering. But what you may also notice is that the update rate is very high, and that's because whenever we reuse information from a cached probe, we make sure that it's also updated with the new Radiance data at the end of the frame, and that's so the state of the cache never falls behind the current state of lighting. And this is applying the LRU sat cache to the render, and you can see that we've fixed our fireflies. All right, now I'd like to get back to this point we skipped earlier, evaluating the lighting at P. This is a very important part of the pipeline. This is where we want to calculate direct lighting on indirect hits, and this is how we complete our path from the eye to the light, and we get our global illumination. We use a mix of two solutions for this, the temporal radiance feedback and hash grid radiance caching. So I start with the temporal radiance feedback. It's really simple. We simply check whether P was visible in the last frame. It's regular temporal reprojection, and if it was, we can use that information instead of the hash grid. Now, because the previous frame's lighting is both direct and indirect lighting, we get some form of recurrent infinite multi-bounce effect for free. Limited though, because the reflector needs to be on screen for this to work, which is nice. This technique is a great way of eliminating many expensive shadow rays, so it's good for performance, but obviously only works when the lighting can be reprojected. So another mechanism is needed for off-screen hits. This image shows without radiance feedback, and with radiance feedback, you can see how it gets brighter due to the extra multi-bounce contributions. And yeah, now we'll be moving on to the hash cells, the second level of radiance caching. So hash grid radiance caching, this is based on spatial hashing, hence the name. It's entirely built on the fly, or another way of saying it possibly is build as you traverse. So we don't pre-build anything, and as we trace our rays, if we hit an area of the scene, we simply look if there's a cell existing. If there is not, we create one. If there is one, we use the existing one. So there's no pre-processing needed. It works on all geometry, and has this nice property of only allocating memory where information is needed, because that's literally build as you traverse, as you hit. In practice, the way it's implemented is associating every cell with a decay value that is being reset every time the cell is touched to the max, and decay to a 0 otherwise. So once the decay finishes, the cell is evicted and its memory can be reclaimed for other areas of world space. This slide tries to explain a bit more in detail how spatial hashing works. It's really simple, very simple technique. We put together what we call a vertex descriptor. We're going to hash it twice. In our case, a vertex descriptor is the quantized position P and quantized direction there, the ray direction in this diagram. I'll explain in just a second why we need to hash twice. But the first hashing function, which we refer to as h1, has to return a value between 0 and our capacity minus 1. And we use this first hash, the result of this first hash, to locate our bucket. A simple linear indexing into an array of buckets. And every bucket contains 16 cells. And we use the secondary hash, which must return anything but 0. That's reserved for empty cells. We use the secondary hash to locate the cell in the bucket. And the reason for this kind of dual hashing thing is that it may well be that you have two distinct descriptors that after applying the first hashing function h1, you get the same value, the same index, which will lead to a conflict. They would share the same radiance, and that may lead to light leaking and such. So the secondary hash is here to perform linear probing and solve conflicts. We perform the probing using atomic exchange to either find or insert a cell in the array, and the resolved cell will store our locally filtered radiance. Now, when we have a new sample, we can add it to the cache by using 4 global atomics that are performed into some pre-cleared scratch memory, later resolved into a half-precision float for reduced bandwidth requirements when looking up the cache. Now, I think it's a good time to mention something about adaptive filtering heuristics. At a distance, the geometrical detail tends to increase, and your view frustum gets fairly large, possibly far beyond your sampling and memory budgets. So we need to find a way to keep memory use under control. And the traditional solution for this is creating LODs, level of details. It's super easy to create LODs with hashing. You simply adapt the amount of quantization, increase the amount of quantization at a distance, in other words, your cell size. We do so in a way that targets a roughly constant size after projection on screen, and we work backwards to derive the size of the cell in wall space. So it means you don't really need to tweak it. It's automatically determined for any scene scale. I'll just jump back to the screen probes for 1 second, mentioning that we apply a very similar approach to our screen probes. That is, we relax the radiance reuse heuristics using a very similar formula at a distance. And this is to make sure we remain temporally stable as the amount of detail increases and the amount of samples reduces. So here you can see this little barrel, how we successfully capture the occlusion and kind of shadow in that little piece of geometry. And as we zoom out, we allow for a bit more blur, a bit more bias, but we can remain stable, temporally stable. All right, now I'd like to talk about filtering in hash space. It's quite an interesting topic. It's quite challenging. We noticed that the occluded regions may exhibit a significant amount of noise under motion. So here the camera is moving to the right, and you can see this kind of blotchy noise coming directly from the noisy hash cells. Now, the size of the cell, depending on how you set it up, is directly proportional to the amount of radiance filtering that you're going to apply. A large cell size means more filtering, so less variance, but more bias, of course. And a small cell size is more faithful, less blurring, but the noise is worse when you don't have enough samples accumulating in the cell. Ideally, we'd like to be able to pick the cell size adaptively, and that's because filtering in hash space can be very costly. We tried simple 3x3x3 kernels, which is kind of the minimum you can do. And this already requires 54 hashing operations and potentially up to 400 reads due to all the linear probing that needs to take place. And it ends up really expensive. So our solution instead is to rely on radiance prefiltering. And in here, what we did is make the hash grid into a 2-level structure. So our buckets now point to 2D tiles of radiance data of 8x8 cells instead of pointing to the cells directly. So 2D tiles, the orientation of the tile is determined based on the direction of the ray of the DIR vector. We simply project onto the XY, XZ, or YZ plane by dropping the largest component from the direction vector. And what's really interesting about this approach is once we have these 8x8 tiles, we can simply prefilter them in a very similar way to MIP mapping. Just calculate the MIP chain. Because they're very low resolution, we can perform the whole prefiltering in LDS, which is pretty fast. And then when it comes the time to look up the radiance cache, we simply pick the correct MIP level for a given noise level. So we're back on our slide, on our image, showing the results without radiance prefiltering. This is a debug view, by the way, showing the indirect lighting only, so the noise is more visible. And after radiance prefiltering, you can see that the noise is nicely reduced. I'll go back and forth. without radiance prefiltering and without radiance prefiltering. Still a bit noisy, but it's a much better result than without the technique. And now we tested this caching scheme across multiple scenes, and we've noticed some scenes may suffer from light leaking artifacts, which is this one here, this bright highlight in the corner should not be there. So we spent a bit of time trying to understand what was going on in here, and this is what we came up with. So what happens here is that the inner green wall, which we reach after bouncing once, well, it's close enough to the outer wall that after quantizing our position, we end up with the same position, like being inside or outside the wall. Now we know our vertex descriptor also includes the direction, but what happens here is that the secondary ray is parallel enough to the bright radiance event that, again, after quantizing the ray directions, we end up with the same direction. So ultimately, this is the same cell we're looking at, whether we're inside the room or outside. So both events will share the same cell and radiance, and that results in a light leak. Now, we found that this mostly happens when the length of the ray is less than the size of the cell. So what we've done is we've extended our vertex descriptor with the Boolean result of the ray length versus cell size inequality test. It's a nice thing about spatial hashing. You can just throw more things in the descriptor and you get new cells. What this does here in this particular case is that it splits the both two events that we've just seen into two separate cells. So we separate out the events and we solve our light leak. All right, so what I've described in the previous section really is mostly how to cache the radiance in wall space. It's still not really how do we evaluate the lighting at P, how do we connect the point P to the light source, and so that's what we finish with. Multiple solutions are possible here. You can use shadow mapping or you can use ray trace shadows. Our implementation focuses on ray trace shadows because we think it's more forward-looking, possibly the right area for us to invest as a research team. But it's worth noting that this system is completely compatible with shadow maps if you have them and want to use them. A very easy way to combine both approaches is to simply make two light lists, one for shadow mapping, one for ray tracing, and add them up. So onto the topic of light sampling. This is really what this is about. How do we pick the best light sample to send our shadow rays? Here I've placed P in a way where it's partially occluded from the surrounding light. So if you were to just do trace rays in random direction, you'll end up wasting many shadow rays that would not hit the light, and this has a strong impact on the variance of the hash cells and ultimately the noise in the probes and the final noise on screen. So we want to do something about this. We could solve this problem obviously by throwing more rays at the problem, but again, we'd like to maintain the ray count both low and constant. So we'd rather try to be smarter about our sampling. And we can use reservoir-based resampling for this, otherwise known as RESTER. RESTER is quite an exciting technique, I believe, for real-time sampling of many ray traced lights. It works out by generating a reservoir for storing the best candidates of a given shading point, and then sharing that structure, that reservoir, to the neighbors through a process known as resampling. And in effect, what you really do is you share the effort of picking the best light candidates across neighbor pixels, so it's cheaper to do. But RESTER's original reuse happens in image space with an image space kernel. And that's a problem because neighbor path vertices are not necessarily close in image space or available at all for that matter. So screen space reuse doesn't work. Instead, we perform our reuse in wall space. This is implemented quite simply by creating a list of reservoirs for every overlapping vertex in a cell. So at the time of reuse, we can simply look up a cell, get the whole list, and pick a random number of reservoirs from inside that list. And we use spatial hashing again to maintain the data structure. Now, RISTA can provide very interesting variance reduction, but resampling really is only as good as the initial state is being fed. If the initial state is not good, then the resampling won't work very well. So we want to work on improving that initial state. We implemented a light grid that's built over the entire scene that helps us pick the best candidates. And every cell of the light grid simply stores a list of the most important lights for that particular cell, for that particular area. This is calculated by weighting every sample based on the illumination they cast over the cell's volume. And we call the lights when the contribution falls below a certain threshold. Now, selecting lights from this structure is quite simple. We simply look up the cell that our vertex lies and pick a random subset from the list, 8 in our implementation. We can use that to generate the reservoir and append it to the wall space cache for further resampling across neighbors. So here I'm showing the result of random sampling. And while RISTA can be very efficient at dealing with many light scenarios, I wanted to highlight here that it can also be really good at helping with noise with a single light source, but that's really hard to reach. In this case, this is our sky, which we can only reach through going through some windows, which you can't really see here, but they're just on the right. So random sampling struggles to produce a clean image, and with RISTA, we're better able to guide the shadow rays towards the light source. And I go back and forth, random sampling, and you can see how RISTA helps clean the noise, although at the expense of some darkening bias, fortunately. All right, now I'll go over the interpolation. How do we interpolate from our probes per pixel and denoise? I've already mentioned more or less how the interpolation path works. We simply locate the 4 neighbor probes for every pixel. We use a depth condition for rejecting invalid probes to avoid light leaking, and we hide the artifacts of the interpolation behind blue noise. So this is our probe grid, and this is the raw results of our interpolation. You can see the blue noise. You can also see that the noise is fairly moderate thanks to our caching system, so we don't really need any heavy denoising. This is the result of our denoiser, which I'll describe now. So yeah, it's very simple denoiser, a bit more like a cleanup pass. I think it aims to be only a temporal reprojection pass because this is what gives the best quality and the least amount of blurring. But reprojection can fail at this occlusion specifically, as we've seen. So what we do is we have the reprojection pass, we have it output both the reprojected color buffer, temporally filtered, and a blur mask, which is fed to an adaptive filter. In practice, we only blur the new pixels for about 8 frames using an ever-decreasing radius, which is what I refer to as the blur mask. For the rest of the pixels, we rely purely on temporal filtering. Interpolation failure. This happens when all the 4 probes we've located, we fail to interpolate from them, or in other words, the depth condition returns 0 for all the 4 probes, which is what's happening if you look at the top image here for those red areas. All 4 probes are like outside that thin hole, sorry. So we're not really, it's not a very good idea to interpolate from any of these probes. Doing so introduces a light leak. But we don't really have a choice because we have no other piece of information. So we do reset all the weights back to 1 in such cases, effectively doing a simple average of the probes, which, as mentioned, introduces some undesirable light leaking, which we fix further down the road by flagging the pixels in the alpha channel, which effectively sends a hint to the denoiser to try and get rid of that sample. And this is a fairly strong hint. We use it in the reprojection pass. If we manage to have valid history, then we get rid of the new sample. If we cannot reproject, we try to get rid of it in the filtering pass, the spatial filtering pass, and if that fails as well, then we output the light leak to the screen, but keep the sample flag in the alpha channel again of the history buffer, so we don't reuse it next frame, so it disappears as quickly as possible. Now I'd like to talk a bit about reaction to light changes. We've noticed that in some cases, if you change lighting condition, the reaction time may be pretty slow. In this case, this is due to using a constant blend factor in our exponential moving average, pretty low blend factor. And a low blend factor is nice because it produces a clean and stable image when the lighting doesn't change, at least. But it suffers from like being very slow to update to changes in lighting conditions. So we fix this by keeping track of the temporally smoothed version of the luminance delta. This effectively gets the luminance of the new sample we've just calculated versus the luminance of the reprojected history. We do the difference, smooth it with the previous delta, and this gives us a very good indication of when the lighting condition has changed. And we can use this to effectively adapt our temporal blend factor, and we simply lerp between a fast blend and a slow blend factor based on the normalized color delta, luminance delta, sorry. This gives stable image when the lighting doesn't change and fast reaction time when it does change. Now a quick note on dynamic geometry and moving objects in general. They generally work because our screen probes use motion vectors for temporal reprojection. Hash cells naturally adapt to moving content. This is, however, not heavily tested path for us still, so more research is needed, and I'll touch upon that a bit in the conclusion again. But we've tried it on like simple objects like here, and it generally works all right. There's more elements that go into the Radiance interpolation, and I don't cover them here for time reasons. I invite you to check out the paper if you're interested, where we have more details. Just to give a bit of an overview, we turned the probes into spherical harmonics prior to gathering the radiance from them. And we also use screen space GI to recover small scale details. Details that typically our probes cannot capture, like less than 20 pixels or so, we can't really capture with the probes. So yeah, we can rely on screen space information for this. We use horizon-based GI, and I'll go back and forth. This is between the two shots, this is the result of our interpolation purely using the probes, and this is with the horizon-based GI. So yeah, back and forth, purely the probes and horizon-based GI, and you can see how the smaller scale details and lighting interactions are better captured. On this slide, I've tried to capture some performance measurements. They're done at 1080p on our latest GPU, 7900 XTX. I'm not going to go over every box one by one. I try to make it so that it's quite visible how much time is spent in each subsystem of the pipeline. And I'll draw your attention only to the final total time of the whole GI pipeline of about 3.6 milliseconds to calculate pretty much all the lighting on this image. And finally, I'll finish with some comparisons with our path tracer, which we use to produce ground truth images. This is set up to perform 3 bounces of global illumination. So yeah, that's the path tracer, and this is the GI1 approximation. And generally you can see that we're quite a bit blurrier than the path tracer, but there is no obvious error, no light leaking, and the intensities roughly match. Here's another example. This is the 3-bounce path tracer, and this is our GI1 approximation. Back and forth again, the path tracer and GI1. And this is a final comparison. The path tracer running on that scene, and GI 1.0, path tracer again, and GI1. All right, with this I'm reaching the conclusion. I've presented a complete global illumination pipeline today that can do diffuse indirect lighting for all light types. We've added the code to perform light sampling from all kind of common light types, spotlights, directional lights, skylights, and so on. And it can do diffuse direct lighting for some lights, such as emissive meshes in sky. We didn't include like doing direct lighting from, say, spotlights and directional lights because, as you've seen with the comparisons with path tracing, probes, they can't really capture anything very high frequency, only like smooth lighting. It makes it a good fit for skylight, for instance, but not a good fit if you want more or less sharp shadows. In terms of future work, our interior scenes tend to be a bit too dark due to the limited support for multi-bounce. So we'd like to look into tracing continuation rays from the hash cells, connect cells between themselves, and get a similar recurrent kind of multi-bounce of a frame similar to our Radiance feedback. Yeah, getting reliable multi-bounce everywhere and images closer to the ground truth. We're also working on adding support for glossy reflections to the pipeline. What I've described really so far can be referred to as diffuse interpolation, where we estimate the irradiance. And we can implement specular interpolation, which is simply sampling the GGX lobe using whatever BRDF you want to use, using important sampling and looking up the probe data instead of tracing a ray to get your radiance value. It works at recovering something that looks like glossy reflections, but as you can see, it's pretty blurry. So we only use this for mid to high roughness surfaces, and we rely on ray tracing shadows for low roughness surfaces and combine both. Finally, another thing we are working on is testing and tweaking the pipeline on larger scenes, especially with more complex animation and things such as foliage and so on. You can find our paper on GPU Open at this page. And this is the list of publications that we've referenced throughout the slides. And that's the end of my presentation. So thank you very much for watching.